Okay, so let us do this Lorentz transformation today. Okay, it is a linear transformation because linear algebra, right? Generally, yeah, you guys are talking about vector space and all that. We can imagine them as coordinate system x, y, z. So once we have a different coordinate system, then we can transform between different types of coordinate system, and that behavior is captured using linear algebra, matrix multiplication from one coordinate into another. So then it is like a matrix multiplication. So that is why linear algebra will cover this a lot. And what we're going to do now is to do something similar, but we do not use linear algebra directly. So let us see how we are going to do that today. Okay, so what we are going to do is to derive the Lorentz transformation laws. So last class on Monday, we have been discussing the concept of time dilation and length contraction, and that also is also derived without using linear algebra. Is just by looking at the concept of how the light travels. Okay, so we do not trust that the time of another person is the same as your time, so we do not assume that the t that Bob uses is the same t that Alice uses, right? We also do not assume that the length that Bob measures is the same as the Alice measures. What we do assume is postulate 2. Postulate 2 is, okay, no matter what experiment that we do, the Michelson-Morley experiment, is that the time of that person is different from your time, but the speed of light of that person will be the same as your speed of light. So we use that as the common ground, and using that common ground, we can derive the relationship between Alice time and Bob time, Alice length and Bob length. So that is time dilation and length contraction. So now we're going to do in a more general setting. Is that, remember last time I was telling you what is the event? An event is time and position. So because time and position for Bob is different, right? For you and for Alice and Bob, and we have length contraction, time dilation, all that. So we want to derive a more precise transformation between these two sets, because the time related things is in the coordinate t, and the position coordinate things like how you get the length of a ruler is in x, y, z. So generally speaking, I have a 4-dimensional vector t, x, y, z, right? So that means for Alice in frame S, she will get four pieces of information t, x, y, z. But for Bob in frame S prime, he also get a different set of 4 numbers, t prime, x prime, y prime, z prime. Okay, so these 2 numbers may not be the same, right? Only the speed of light will be the same. So how do we make sure, how do we figure out how to transform between one frame to another? Since we have learned time dilation and length contraction, we can actually derive the transformation between the two. So that is what we are going to start with today. Correct, yes. Yeah. So it's exactly like a 4-dimensional vector space, because x, y, z, this one is like a row vector, right? A matrix with one row, and similarly for this as well. Okay, so that is what we're going to do. So before we actually, right, what we're going to do is we're not going to derive the most general situation. That will be very, very messy. Let us start with some simplifying assumptions. Okay, so what's our assumption here is that our assumption number 1 is the Bob's frame is moving relative to Alice S in the x direction only. So we do not worry about the y and z direction for now. Okay, so only horizontal motion between Bob and Alice, right? There's no vertical motion, or there's no z direction motion. Only Alice and Bob only moving along the z direction. Okay, and the relative speed is, we call this u. Is u. Okay, so in other words, right, Alice will see Bob moving at velocity u. Bob see Alice moving at velocity negative u. Okay, so that means I should write this out, right? Alice sees Bob moving at velocity positive u. Then Bob sees Alice moving at velocity minus u. Agree, right? Yeah, because relative motion, right? If you're in front, you see positive direction, but if you're the other person, you see the person going the other way, so it's the negative direction. Okay, so along the x direction. Second assumption is we will synchronize our watch between Alice and Bob at time 0. So both person have the watch start from 0 together at the same time when their origins are the same. So origin of S and S prime are the same at time 0, and both of them start at the same time. Okay, so in other words, 0 x y z will be equals to 0 x prime y prime z prime, only at this time. Then as time goes on, then it's going to be different already because of special relativity, time dilation, length contraction. Okay, so we can only synchronize a starting point, right? So we let the two we give them two identical watches, and then Bob will start to move, right? And then Alice stay on Earth, like the spaceship twin paradox situation. So this is our starting assumption. Okay, so we got this now. Then now let us try to calculate. Oh yeah, another thing is, well, let us say the origin is where Alice and Bob are located. So we are going to say that let Alice be located at the origin of S, at the origin of S, and then Bob located at origin of S prime. Okay, so both persons observe an event P. Okay, so the event, which we will call P, right? So P is an event, that means something happening somewhere, so there's a time and place where it happens. So Alice will observe some time and some place, Bob will observe some time and some place, and we see how they are two related to each other. Okay, so yeah, so let's say, right, if they are both located at the origin, that means how far away is the event P from Alice and from Bob? So these statements are definitely straightforward. According to Alice, okay, so according to Alice, P is at a distance x away from her. Okay, so if you're Alice, right, so if you're Alice and I try not to draw because every time we draw a diagram, right, we are assuming some perspective. So actually I'll just draw Alice frame. Yeah, so according to so Alice is here, right? So the event P is here, right? So the distance of P away from her, we don't worry about time yet. We are just talking about distance, right? So this is Alice frame. That means the distance is P away from her. So what I'm trying to say and what I'm trying to convince you is this value of x is the proper length in S. Okay, this is important because we need to remember later this will not be the proper length S prime. Okay, so the distance that we got here is the proper length in the frame S, okay, because it will not be proper length in the other frame. Okay, so we got an event P, right? So we got an event P, and then that is the length, the distance between Alice and the position P. So then we can say the same thing about Bob. According to Bob, right, P is at distance x prime away from him. Okay, so this is now, we are now drawing a picture of Bob here, S prime, and then P. So Bob using a separate coordinate system, so he's going to get some number x prime. So the distance between him and the point P is x prime. So this number here is proper length for Bob in S prime. Okay, so important to remember, because these two are moving relative to each other, this length will be not the proper length for as seen by Alice, right? So Alice will see this length as length contracted, so not proper in S, right? So when you are not having the proper length, then you are observing the length contraction. So the formula for length contraction we have derived on Monday, right? Okay, so we're going to use that later. Okay, so yeah, so everyone agree with this setup now, right? It's pretty basic, okay, but it's going to well, I don't know if it's going to get more complicated, but you will get the special relativity results later, the Lorentz transformation. Okay, so if everyone agrees with this setup, let us see what Alice measure. Okay, did someone ask anything? Improper in S. Oh, what I was talking about just now, right? Yeah, proper in S, improper in S prime. Oh. Oh yeah. You're right. I'm missing the word not. Not proper in S prime. Not proper in S prime. The distance parallel to X, correct? Yes. Yeah, the horizontal distance. Yeah. So we're just only focusing on the X coordinate. Just proper for the observers. Yeah. Yes. Basically, yeah. Is it getting more tricky for you? But you get what's going on now. So that's good lah. That's good. The S is in terms of X, Y, Z. Correct. So so a frame S, right? Every time we say frame S, is a frame has a coordinate system, right? So this is a coordinate system S. So I got the X coordinate, I got a Y coordinate, and then I got a Z coordinate, right? So that is a frame S. Then and also there's also a time T. So a frame S is a coordinate system and also a clock. So it will measure T. Right. So this is my picture of a clock. Okay, so that is the 4-dimensional vectors. I cannot draw 4 dimensions here, but I can draw a watch, right? So basically, yeah, it's actually not as complicated. It's just like position and time. And I believe, you know, speaking of Stephen Hawking's book last time, right? In the brief history of time also, he mentioned something like that. If you want to specify some information, right, you always need 4 sets of numbers. If you want to attend your birthday party of someone, right? So birthday party of someone, then the party is the person's birthday at 8 p.m. and then the house address. So house address, to go to the correct place, right? Yeah, we have address and everything, but fundamentally you need 3 sets of numbers to go to the correct position, right? The GPS coordinates, right? Then 3 sets of numbers. And then to make sure you do not miss the party, you need to go at 8 p.m. So you need the 4th number, right? So I have 4 sets of number. It's just 4-dimensional vector space. And if you write out the 4 pieces of numbers is here. Okay, so that is all we are covering here. In this case is, yeah, so right now we are only focusing on the X direction and also the time. So 1 plus 1D. Why X is proper in X prime? No, it's not constant in time. For the moment, yeah, okay, so we need to start to think time as another coordinate as well. So an event is happening at one moment in time. So an event P, right, event P is the birthday party, 8 p.m. right? Maybe it's a very short party, 9 p.m. settled, gone already. So this birthday party is happening at this place, okay, and at 8 p.m. Okay, so we are not saying whether it's constant in time or not. It's not relevant, because this is at some moment in time. Okay, remember event includes the time. Okay. Yeah, instantaneously, yes. So if you do calculation, yes, yeah, so this is what we are about to do now. Yeah, so we are about to derive a formula in how to relate this one frame to another frame, right? So this is a set of coordinate systems, and a moving person will have a different coordinate system, another moving person, so we want to derive the relation between this measurement by Alice and this measurement by Bob. Okay, so that is the setup, right? So this is the situation that we have, and yes, to answer Zuri again, yeah, we are only considering the x direction for the moment. Yeah, we put the y and z direction aside, right? Let's focus on the x direction first. Okay, so let us calculate this part. So let's say, what does Alice measure? Okay, so Alice measures Alice measurements. Okay, so Alice measurements is this. Correct, each observer measures own length. So I define proper length on Monday. The full definition is the proper length is the length of the object in the frame where it is at rest. So yeah, so we define it on Monday. So Alice measurement is the following. Okay, so what does Alice see is, okay, so now I will draw both frames, because now I can remember that we are talking about Alice specifically. So Alice is here, okay, so fine, yeah, right. And then Bob is on the frame that is moving relative to Alice. So let me draw Bob here. Okay. And the distance between Alice and Bob is increasing because Bob is moving at speed u. Okay, so the distance between Alice and Bob is ut, right? So Alice is measuring time t and position x, right? So according to Alice time, at time 0, Bob is with her, and then after that Bob is moving, right? So as time goes on, Alice will see Bob going further and further away. So Bob is going further and further away from Alice as time goes on, okay, at speed u. So the distance between these two is ut. So as I said, right, both persons observe event p, right? So and what I said just now, that according to Alice, where is the event p? So the event p happened at a distance x away from her. So this is x, right? And of course, Alice is here, event p is there. She can measure how far away that is. So this is the proper length for Alice. Okay. Now, I also said, right, according to Bob, Bob says that event p is x prime away from him, right? So away from him, then x prime is Bob's proper length, but it is not proper length if we are talking about Alice, right? So what is this distance from here to here? Okay, so what is this distance? Is it x prime? Not really, right? Not really, because this is not the proper length. We are talking about Alice. According to Alice, how far is this interval? How far is this length? It is x prime over gamma, length contraction. Yeah, contraction. Do you agree? Yeah, so it's going to be yeah, the x prime must be divided by u gamma. That's the length contraction. Okay, so that is the new thing. Okay, remember when in chapter 1, before we start talking about relativity, the Galilean transformation, yeah, right, is in chapter 1 is x prime for Bob, right, and then this is equals to this plus this. But this length, right, is actually length contracted, so we got this value now. Okay, so all the frames here are the result obtained by Alice, so we can, it is in the same coordinate system, so we can sum them up. What I'm trying to say is we have found that x is equals to ut plus this length. So this length is undergone length contraction. Okay. Yeah. So I don't know how far do you agree with this, right? But that is how. So now we can derive our first Lorentz transformation. So we got this relation now, the relation between Bob's measurement and Alice's measurement. So we can actually solve for x prime. So x minus ut is equals to x prime over gamma. So I can use this calculation to expect what Bob will obtain, right? So what Bob obtained is related to this is gamma x minus ut. Okay, so this is our first Lorentz transformation. So we have found the relation between the x from Alice and what does Bob get, right? So these are the relation between the two. We also need the time. So at event t, right, is something happening in a certain time, so we need to input a time, right? So that's why I say just now, it doesn't matter whether this length is constant in time or not. It's like one time in this specific time, right? We don't care. We will care later, but for now is this relation. Okay. So yeah, so let's call this equation 1. Okay. So this is a relationship between x and x prime. So what we're going to do next is, how about the time coordinate? No, it's not the same. Yeah, t is not the same. It's not the same. Okay. So Alice is t, Bob is t prime, right? And we do not expect them to be the same because the time dilation, right? The time for Bob observed by Alice is slower, and so on and so forth. So like what we did on Monday, the time dilation. So time is not the same for both of them. This is Alice. This is Bob. So time is not the same, but the t here is the time for Alice, right? So we're talking about time for Alice. This is x for Alice. And then position for Bob is x prime. You mean you blur, everyone is blur about everything, or blur about why the time is not the same? The whole thing, okay, I'm trying to go as slow as I can. Why time not the same? Yeah, so this one is you refer to the Monday lecture, the length contraction. So you look up the Monday details. So why is time not the same? Yeah, so remember on Monday, right, we were discussing time dilation, right? Time dilation is like I have the clock. One of the clock is running slower. So you know, you can reset your clock, right? You can set the time, you know, set the timer to be 0. I want to show it. Yeah, so let's say I got the, yeah, so let's say I have a second, Alice and Bob have 2 clocks, right? And they both of them, they start at 0. Oh yeah, they both start at 0, right? But so you have 2 clocks. I only need the starting point to be the same. That means we just start the same. Okay, but then because of time dilation, right, Alice will see Bob's clock running slower. Yeah, so I hope that yeah, so that is the important point, right? Time only start at the same number 0, but they run at one clock is slower than the other. Both clocks are the same. Okay, so just to recap, right, y divided by gamma is because of length contraction. So if you observe another person's frame, if you observe a ruler on another frame, right, the ruler appears shorter to your perspective, right? Shorter by how much factor? By a factor of gamma. So if you observe the coordinate length of Bob, then Bob's rulers measure shorter, right? So in Bob's frame, right, Bob is using his ruler to measure the distance between P. So Bob using a ruler, and according to the ruler is x prime. But from Alice's point of view, right, Bob's ruler looks shorter. So that's why x prime divided by gamma appears shorter. They are moving in velocity u. So it's not unknown, but it's just some number u. U can be any number. Okay, just plug in like how many meters per second. Yeah. They are moving with unknown velocity. So it's not unknown. Alice see Bob moving at velocity positive u, therefore Bob see Alice moving at velocity negative u in so remember, right, we are using a coordinate system, so u is dx dt, and Bob will use coordinate system x prime dt prime. We will actually calculate the velocity transformation later. So the starting point is the same, delta t is different. Correct, exactly. Yes, that's what I was trying to say by taking out my phone and stuff. So both start from 0, but yeah. You imagine you have two watches, right? If one of them has low battery, then the clock will not always show the same time, right? Even though at 12 o'clock both are the same, but then if you give the second watch a low battery, then it will run at a different, it will be slower than the other watch. Okay, so that was Alice's measurement. Okay, relating the two. So t, we are talking about the time measured by Alice. So what is Bob's point of view? So Bob's measurements. Okay, so what does Bob see? So we're drawing the situation again. Now we focus on Bob. Okay, so Alice is here, Bob is here, both observing an event. Okay, so the distance between Alice and Bob is still ut, right? I'm talking about the distance only, so the how far away it is still ut, but ut prime. Okay, we're now talking about Bob's time and Bob's position measurement, right? So a clock used by Bob, and the coordinate system is the ruler and all the axes used by Bob. Okay, so yeah, that's why time is not the same for both of them. Must not be the same. This is special relativity. Time works differently for different people now. Okay, so Bob is here, Alice is here. Both of them measure the same event P. Okay, so we are using Bob's coordinate system now. So now the distance between Bob and P is of course x prime, yes. So this is the proper length. Right, x prime is the proper length in Bob's frame. Okay. Correct, yes, exactly. Bob is moving relative to Alice. Yeah. No, velocity is different direction. No, we can't say that because we only have two perspectives, right? We can only see what Bob is doing and the point P. So it's not because they're different direction, but they are moving relative to each other. Okay, so how to compare V? Yeah, so V is something we'll calculate later. It will depend on the value of the velocity, yes. So in the meaning the U appear in the equation here. So U is the relative velocity, a relative speed, right? So it depends on U. Yeah, so in that sense, it depends on this. Yeah, relative. We'll call this relative speed. Okay, I'm taking the magnitude of U here. In any case, right now we got this now. What is the distance between P and Alice? Okay, so you're Bob now, right? You're moving away from Alice, and then you see the event P there, right? So you see the event P, and then you see Alice. So how far is the distance between P and Alice? Because you're Bob, right? Alice is moving away from you. Okay, so so Alice is on a different frame. Then Alice say her length was, her distance between her and the event was x. So what is the distance that Bob measures? Right, it's not x anymore, but x over gamma. Right, so because we got the length contraction. Okay, so this is not a proper length for Bob, right? Because Bob is moving relative to this length. So if you are moving relative to a length, then it's not your proper length already. Okay, so this is the length contraction. Okay, so yeah, then everyone agrees with this now, right? So now I have made sure I gotten all my values using Bob's frame. So this length is equals to this length plus this length, right? So in the same frame you can add up the length. I make sure that the Bob's length is x divided by gamma, so that is Bob's measurement, right? So we got x over gamma is equals to ut prime plus x prime. See, must not say they are the same. I need the t prime to be different. I need the relation between t prime and t. That's what we want to do. Okay, so I got these two relations now, and then let's call this equation 2 because I'm going to substitute the x prime into here. Okay, so I'm going to substitute equation 1 into 2, and then let's see what we get after substitution. Okay, so I got x over gamma is ut prime, and then I already know what is x prime. X prime is gamma x minus ut. So after I substitute, I can now derive a relationship between t prime and t, just solving for t. Okay, so solve for t. X over gamma on the left hand side is x. 1 over gamma is this, right? So remember, gamma was the Lorentz factor. Okay, so x over gamma is actually this, and then ut prime is this. So this is x minus ut over gamma. So gamma is 1 minus u squared over c squared. Right? Agree? Okay. So I want to find what is the formula for t prime. So I put t prime on one side of the equation. I bring this over. So x square root 1 minus u squared over c squared minus x minus ut over this. Okay. How the u can be measured? Just the straightforward way, because u is just Alice look at Bob, and then she see how Bob is moving away from her. So you can get the speed between Alice and Bob. That is u. A travel relative to B, so this one is not proper to both. No, so u is the common ground between the two. Yeah, because we are okay. So in Alice coordinate system, right? In Alice's coordinate system, because it's these 2 points, Alice and Bob, right? They are not observing a third point. So if you're observing a third object, then they might disagree, but it's just between the two of them. So if you're using Alice's coordinate system, then using her distance and her time, she will get u. And then from Bob also, using Bob's distance and Bob's time, they are different, but it's also u, because it's just how far Alice is moving away from her. So u is the same for the both of them. The magnitude of u. Okay? Because it's t prime. It's just the time is different, right? So ut and ut prime. Okay, huh? Yeah. So okay, so if everyone agrees with this, then this one is just manipulation, so that one shouldn't be a problem. Just simplify the equation. It might be messy, but it's just the stuff you learn in high school, right? How do I subtract the two? Make the denominators the same. So I make both denominators to be 1 minus u squared over c squared. So I times this by the square root, so it's 1 minus u squared over c squared, and then minus x minus ut. Okay, so what I got here is actually x minus u squared x over c squared, and then I got minus x, and then I plus ut over here, and then the whole thing is divided by 1 minus u squared over c squared. So actually the x cancel out, and I have ut minus u squared x over c squared divided by, so this thing is actually just gamma, right? And then this is ut prime. Okay, so u is the same for everybody, right? So I can actually divide both sides by u, and therefore I find that my t prime is just t minus ux over c squared divided by gamma. So let's just write this as gamma, so that my t prime is gamma t minus ux over c squared. So I have derived, now this is the relation between the times, and this was the relation between the position. So we have gotten the Lorentz transformation formula already. Okay, so this is the relation between the times. Okay, so now we know, right? If I know how fast Bob is moving away from me, right, then whatever time I observe, I can calculate what Bob will get, right, without having to ask him, because I can use this formula. Then I will know what Bob will measure. So this is a very useful formula. Lorentz transformation is what we are trying to do now. Okay, what we are doing, this is the topic of this, the name of this calculation. It will make sense after I write everything. So let me compile all. Oh yeah, I forgot. Okay, so since we are talking about motion between x direction, right, then we are ignoring y, because there's no effect on the y direction. There is no relative motion in the y and z direction. So therefore, so we are only talking about the x direction. So there's no vertical motion between Alice and Bob. If there is no vertical motion, then the measurement by Bob in y is the same as Alice. So these are the so these are our results. Okay, so now I have 4 equations. So collecting our equations together. Okay, so what we have here is that the t prime, the measurement of Bob is given by gamma t minus ux over c square, and then the x position measured by Bob was here, so it's gamma x minus ut, and then Bob's measurement in the y direction is the same for Alice, then z direction is the same for Alice as well. Okay, and of course gamma is the Lorentz factor given by this formula, and u is the relative motion between the two. So this whole thing, this set of equation is called the Lorentz transformation. Lorentz. Okay, and this is for relative motion in the horizontal x direction. So Lorentz transformation for relative motion along the x direction. Okay, so if it's transformation along the x direction, then the x position are different between Alice and Bob. Time is also different. Then the other directions are not affected. Okay. So that means, right, this is a assumption for x direction only. So how about, let's say if I want to do the Lorentz transformation between the y direction. So for example, right, for relative motion along the y direction, then the transformation is just t minus uy over c square, and then x prime, because y direction, so x is no longer affected, but the y should be y minus ut. Well, there's still no z motion, so z is here, and gamma is the same. Okay, so it depends on what direction is your relative motion, then you will transform accordingly. We know how to determine proper x. Can we know how to calculate? X and t are the same. Proper x is your ruler, right? Proper t is measured by the clock. So yeah, it's the same thing. I mean, if you know in one frame, then that is the result of that particular frame. Okay, so this is the so this is the Lorentz transformation formula. In x and y, you mean x and, so there is relative, it's like you mean diagonal motion. So Bob is moving x component and y component, right? So there's some diagonal motion. The formula is going to be more complicated. I can't even, you need vector, you need to write this in vector form. Do I have it here? Yeah, it's in the lecture notes now. So in vector, yeah, so you need to write it in this way. So the R vector has x, y, z components, so you need to write it in this way. That's why we are not doing it here. It's more easily performed. Actually, yeah, because once you got this right, to get the velocity is actually easy. This is the hard part. The velocity is what we are going to do next, right? Because the hard thing is to get this in the first place. Once we get this, then we just use the formula only. Then that's it already. We just use the formula. So that's what we are going to do next. Before we run out of time, we are going to move on to 10.3.4. Lorentz transformation. So this is for coordinates, for position and also time. Now we want to see the velocity measurements. So Lorentz transformation for velocities. Okay. Any other question before we move on to the next part? Yeah, it's going to be easy because we are just going to make use of this formula. In fact, yeah, this formula. Okay. So right now, right, just now we measure the position and time of an event. Okay, but let's say Alice and Bob is observing a moving particle, right? So at different times the particle will get different positions, and from kinematics you can get the velocity and acceleration if you know how the position changes with time. So how do we do it for the case of special relativity? Okay, so that's what we're going to do. So we'll continue to assume relative velocity, Alice and Bob, along the x direction. Okay, so then yeah, so as before, right, Alice is using frame S, so her values I will label them by t, x, y, z, and then Bob is using frame S prime, so t prime, x prime, y prime, z prime. Okay, so these are the two numbers that yeah, so that's the thing about special relativity, is we do not assume an absolute time anymore or absolute velocity anymore, right? Based on the question you guys are asking, you are still thinking in that way, so we need to stop, abandon this kind of thinking, right? What I'm saying is, when you guys frame the wording like, oh, if Bob is moving, right, it's not really Bob is moving, but Bob is only moving according to Alice. But if you are Bob, right, you are always in your position the whole time, right? So that is the coordinate system you are using. So Bob is at rest in frame S, but Bob is moving in frame S. Hang on, yeah, say again. Bob is at rest in S prime, not at rest in S. Then conversely, Alice is at rest in this frame. Alice is not at rest in this frame. Okay, so that's what I'm trying to say. Okay, so when you say Bob is moving, you should extra say Bob is moving in S. Bob is not moving in S prime. Okay. The world, no, that's kind of thing, right? That's the kind of the point. The world doesn't revolve around anyone, because only in S, the world only revolves around Bob in S prime, only in S prime, right? No longer in S. And similarly, right, the world revolves around Alice in S, not in S prime. Exactly, yes. So we stop thinking relative to the Earth. Yeah. So imagine if you are in space, right? Then there's no reference point anymore. Okay, your reference point is only your own spaceship. And if you observe Alice spaceship, then you have two spaceships of reference points. Then you cannot tell the difference between the two. What about the sun? Well, the Earth and sun is actually another reference point, right? So you got S, S prime, S1, S2, S3. So every object is a reference point. But if then the special relativity or the transformation is still applying between the two. Okay, so yeah, so in any case, we have the transformation law, right? So we've got T prime is gamma T minus Ux over C square. X transform will be gamma X minus Ut. And then, yeah, Y is the same, Z is the same. And now we are observing a moving particle. So Bob is in S prime. So Bob is in the origin. So Bob is at rest in this frame. But Alice is at rest in this frame. So this is S, right? And let's say we are observing a particle that is moving. Okay, so it's moving. This is point P. Okay, so this is at instant in time. Even if we say instant in time is T prime for Bob and T for Alice. Okay, so what is the velocity of this particle? Okay, so this is what we're going to do. Okay, I have no space to write here, so let me write this another time here. Okay, x prime is gamma x minus ut, y prime is y, z prime is z. Okay, yeah. Is there any more question? Sun is too small. Yeah, I yeah, so the myth of the 9 suns, right? Actually, it's something that you can write a science fiction version of that story. It might be an interesting retelling of an ancient myth, right? Because even Sherlock Holmes, it was originally written in the olden days. Then now you can have the modern day Sherlock. So why not do the same thing for other myths as well? Okay. So yeah, how do we measure velocity? To get velocity, right, I need to know the changes, so infinitesimal changes. Okay, so that means I need to know the differential. So dt is, just take the differential of both sides, right? So dt is dt minus u dx over c square, and then the differential of x prime, you just take the differential of both sides. This is an equation, right? So we can do this. And then the y is the same, so it doesn't matter for y. And doesn't matter for z, it's the same. Okay, so yeah, so according to Alice, point P is moving at velocity velocity v measured by Alice. Okay, so what I'm talking about is there's a xyz component, so there's a vx and then vy and then vz in the k direction. Okay, so what is vx? Vx is the rate of change of the x coordinate with time. Vy is the rate of change of y coordinate with time. Vz is the rate of change of z coordinate with time. And here we are talking about Alice, so we are using all the coordinates in the Alice frame. Okay, so we are using all the coordinates in the Alice frame. Okay, so like this. Then what is the velocity measured by Bob? Okay, so let's say if you're Alice, you measure this value. So what will Bob measure if you just know this information? Okay, so we can actually calculate this. So yeah, so let us derive this. So for measure, so let's the x component. Yeah, so start with the x component. Velocity measured by Bob, which is Vx in Bob's frame. So if we are using Bob's frame, right, I'm doing the rate of change of x and t, but the coordinate measured by Bob. So this is t prime, x prime, and y prime, z prime. Okay. Okay, so this is dx prime, dt prime. So what I'm going to do is, well, my dx prime is given by this. So this is gamma. And then my dt prime is given by this formula. So gamma dt minus u dx over c squared. Okay, so I can cancel the gamma and I can take out a factor of dt. So take out a factor of dt top and bottom, so I got dx dt here, and then u like this, and then downstairs I take out a factor of dt also, so I got 1 u over c square dx dt. Okay, so I can cancel the copy of t, right? And if I do it this way, then I recognize this is the velocity measured by Alice, this is the velocity measured by Alice. So the relation of the velocity measured by Bob in terms of Alice result is given by Vx minus u divided by 1 minus uvx over c squared. So this is the transformation in Lorentz transformation for velocity. So given the velocity measured by Alice, we can actually calculate what Bob will get, right? Don't have to ask him, right? We can calculate and see what we get. Oh, okay. Yeah, so by the way, now is the time to take a break, and I will use this time to read what you guys have been talking about. So let us take a 10 minutes break and let everyone digest this Lorentz transformation, and we continue in 10 minutes time. Right, so take a 10-minute break. Okay, so I will stop the recording. Yeah, by the way, talking about assignment, yeah, it's a good time to remind everyone that assignment is due on, like Charles said, is January 15, Friday of next week. So next week is our final week already, and then after that exams will be coming soon. Okay, so yeah, now is a good time to start preparing and get ready for exams and all those things. If you have any questions about the assignment, ask me. I already uploaded the sample, so you can see the sample and get a picture of what we can how do you write the report, right? I think, yeah, depends on when is your exam, but some of your exam might be quite early, 25/1. So you do have 1 week, is it? Actually the exam timetable is out, so we can check. I haven't checked yet, so you can check your exam timetable in your AC. But now we should continue because we still have a lot of things to talk about, especially about the Lorentz transformation. Okay, so this is the transformation between the x direction. So then let me ask you the question, what is the y velocity, the velocity in the y direction okay, so what is the y velocity measured by Bob? Can you say the velocity in y measured by Bob is the same measured by Alice? It will not be the same. Okay, so it will not be the same. So let us see why. Okay, because the velocity of y measured by Bob, right, is using Bob's coordinate system, dy prime dt prime. Yeah, so I think that now it makes sense. Yes, next week is the final week of classes, then study week, then exam 25/1. Okay, so the velocity in the y direction is also affected, and because, okay, so now look at the infinitesimal changes. This is the transformation between Alice measurements and Bob's measurement, right? So the time is affected, the position of x is affected, y is different. But if you talk about velocity, right, Velocity is the rate of change with respect to time. So this time is affected by Lorentz transformation. So even though the y is the same, but the dt is different. So if I divide these two, right? So what I have here is this is dy, and then same for Alice and same between Alice and Bob, but the dt for Bob is different from Alice. So dt is transformed, u dx over c squared. Okay, so if I take out a factor of dt, so I got dy, then I got dt, and then gamma, so this becomes 1 minus u over c squared dx dt. Then we recognize that this is the velocity on the y direction measured by Alice. This is the velocity in the x direction measured by Alice. So the Vy prime is actually related to Alice by Vy, but not just Vy, but divided by gamma 1 minus u Vx over c squared. So the y velocity is affected also for velocity, because velocity involves time. That's why time is different for Alice and Bob. So the velocity that they measure will also be different. Okay, so similarly, right, you can do the same thing for the z direction. It's the same process, so no need to spend so much time. I'll just show you here. U Vx over c squared. Okay, so this is when the particle can be moving in any direction, x, y, z, right? We're talking, that is point P. But Alice and Bob relative velocity is only in the x direction. Okay, so I have 3 objects over here. Correct, yes. It applies regardless of position on P. Yeah, because what we are actually doing is the rate of change of position of P with respect to time. Right? So position of measured by Bob divided by time measured by Bob. Yeah, so here is, yeah, this true is regard. Velocity is a separate thing from position, that's why. Okay. So let's look at an example. Okay, so let's do 10.3.4. A spaceship is moving away from Earth at 0.9 c, fires a robot space probe in the same direction as its motion relative to spaceship. So we can assume that all is happening along the same direction. Let's call this direction x. Okay, what is the probe's velocity relative to Earth? And part B, we will do it later. Okay, so let's focus on this part first. Close and solve. So example 10.3.4. Okay, yeah, right, every time when you solve a relativity problem, there's always going to be a frame S and a frame S prime, and one of them is going to be at the point P. So you just need to identify who is who. Okay, so what I'm going to do is I'm going to take Alice to be Earth. So Alice is the observer on Earth, and Bob is on the spaceship. And the spaceship launches a space probe. So that is a third object. So P shall be my space probe. Okay, yeah, so I got Alice on Earth, and then a spaceship where Bob is inside here, and then it launches a probe. So point P. This is Bob, this is Alice. Okay, and given this information, the relative speed, well, the spaceship is moving at u away from Earth, so the relative speed is 0.9 c, right? And then the space probe is launched away from Bob at 0.7 c, so 0.700 c. So this shall be the velocity measured by who? By Bob, right? Not Alice. Okay, but what we want to do is we want to calculate what is the velocity measured by Alice. Okay, so yeah, so we shall be using this formula. Vx prime is actually Vx minus u 1 minus uvx over c square, right? And then just plug in the information. So I got 0.7 c, this is Vx is unknown, this is 0.9 c, and then 1 minus 0.9 c, and then Vx is 0.7 c. Hang on, Vx is unknown, x prime is 0.7 c, and then this is c squared. Okay, so I can cancel one of these factors, right, and simplify. So I multiply this factor over, so I got 0.7 c minus c, and this c will cancel, so it's going to be 0.7 and 9, and then I got the Vx here, and then I got Vx minus 0.90 c. Okay, so I now bring this over now, so I have 1 plus 0.7.9 Vx, and then this is 0.7 c plus 0.9 c. So finally we can get Vx. Okay, so Vx is 0.982 c. Okay, so that will be the speed measured by Alice. Okay, so let's move on to part B now. Now I have a separate thing. A scout ship is sent to catch up with the spaceship traveling 0.9. So I have another object, a scout ship. So another object. So another little ship here. Okay. This is the scout ship. This is the probe. So I'll just call this point P2. Right. So then another point is the scout, right? So the velocity of this P2 point, this scout ship, is measured by Alice to be 0.95 c. Okay, so what we want to find out is what is the velocity relative to the spaceship. So we just need to know what is Vx prime using this thing. Okay, so using the formula again, Vx prime is just the speed measured by Alice, 0.95 c, minus the relative speed between Alice and Bob is 0.9 c, and then 1 minus 0.9 c, and then 0.95 c over c squared. So I can actually cancel all these terms and then calculate and simplify. So this is going to be 0.05, and then downstairs is going to be 0.145. So this is 0.345 c. Okay. Yeah. So getting the formula is very tricky and hard to understand, but once you have the formula already, you just need to decide who is Alice, who is Bob, who is the P, put everything correctly, then the rest is just getting in the number, right? So it's pretty straightforward after that, right? So after that step is going to be pretty straightforward. Okay, so yeah, so that is the example. Now, having the Lorentz transformation, right? Let's look at this. Okay, so let me study some further properties of Lorentz transformation. Yeah, so some further properties. So I just want to focus on this formula. I'll just write it this way. The first property I want to discuss is how is it related to the Galilean transformation. Okay, so in chapter 1 we learned the Galilean transformation formula, right? Just the direct sum of the two velocities. But now I got a different set of formula. So how can I have two different formula? They are actually related. So what I want to discuss is the reduction to Galilean transformation. Okay, so my full formula is velocity measured by Bob is given by Alice result minus the relative speed, and then 1 minus uvx over c square. Okay, so remember, right, special relativity is because, yeah, it's all this formula, but when we talk about Newtonian mechanics in chapter 1 and 2, how come we can ignore special relativity there? The reason is because when we study problems in chapters 1 and 2, the velocities there are usually very small compared to the speed of light. Okay, so let's see what happens. If my speed, like let's say my relative velocity is much smaller compared to c, so if my two frames are moving at some speed that is much smaller than the speed of light, then what happens to my transformation formula? We notice that there's a u over c. So if u is much smaller than c, so u over c square is a very small number. So it is negligible, right? So if v is a very small number, then vx prime is approximately vx minus u, and then this one is 1 minus a small number, so it's like still dividing by 1. So we conclude that vx is approximately vx minus u. Okay, so this is back to the Galilean transformation. So in other words, if the relative velocity between Alice and Bob is very small compared to the speed of light, we come back to the Galilean transformation formula. Okay. Testing. Test. Okay. Okay, yeah, I was like kind of wondering, like my spider sense start to go off when there's a equipment failure start to happen. Okay, so yeah, so it's consistent with Newtonian consistent with our usual Newtonian mechanics. So Newtonian mechanics happen when u is very small compared to the speed of light, right? So yeah, remember all the problems we saw in Newtonian mechanics. People talk about tennis ball, right? Dropping objects from the building, so it's like 10 meters, and then the acceleration is 9.8 meters per second. So the fastest speed you can go is 10 meters per second, or a few hundred meters per second. Even the speed of sound, right? 340 meters per second is much slower compared to the speed of light. So all the Newtonian chapters 1, 2, 3 we have been discussing is consistent with the Galilean transformation. Okay, but the true formula, right, when for all velocity, whether it's close to the speed of light or small, then we can always use this formula. So the special relativity is, that's why people say special relativity replaces Newtonian mechanics, because it's a more general formula. It contains Newtonian mechanics as a special case. Yeah, so okay, so now let's talk about the speed of light, okay, and the Galilean transformation. So where does postulate 2, according to postulate 2, right, Alice and Bob measures the speed of light in the same for both frames, okay, and then we got the velocity transformation between the two frames. So now we can actually test our formula. So let's see what happens if Alice and Bob measures the speed of light. Okay, so in this case, my P, this means that both are observing P, so P is light itself. So we want to measure how fast this light is traveling. Okay, so we're going to let P equals to light. and then Alice observes light to move at Vx, right? So Vx measured by Alice. So let's say Alice measures C first, okay? So if Alice measures C, what does Bob measure? Okay, so we can, if Alice measures C, we can use this formula to get what does Bob measure. Yes, correct. Yeah, because C is much larger than U, so this is going to be a small number. So in all your Lorentz transformation, if you see it becomes small number, it becomes your ordinary Galilean transformation. By the way, yeah, so Alice observes speed of light, so Bob measures. Right, so I'm going to use this formula again. So the formula measured by Bob is Vx prime is, so speed that Alice measure is C, relative velocity between Alice and Bob is U, okay, and then 1 minus U, and then this is C over C squared. Okay, so I can cancel this, and what I find is C minus U over 1 minus U over C squared. Wait, I already cancelled the square, so I got this now. Right? Then, yeah, so I can this term actually can simplify, right? Because C minus U, I can take out a factor of C squared, so this becomes C minus U. Then I can cancel the 2. So my Vx prime is just 1 over C, so Vx prime is equals to C. So Bob also measure the same C, right? Alice measures C, Bob measures C. Is inside this Lorentz transformation. So same. So it agrees with postulate 2. Of course it agrees because we derived the Lorentz transformation using postulate 2 in the first place. So this is not a proof of postulate 2, but just to make sure our formula is correct. Yeah, Newton did not notice this. Yeah, so at that time, right, nobody noticed this because at that time they don't have the technology to measure the speed of light, right? And we needed the Michelson-Morley experiment to confirm that no matter what frame you use, you actually measure the same speed of light, no matter what happens. So, and this is only happening at very, very high speed. So that is one of the issues to consider. The next thing I want to discuss is the inverse transformation. Okay, so my inverse I start with this formula, right? So Vx minus U, okay, 1 minus U Vx minus C square. Okay, so how do inverse transformation means invert. So I want to solve this equation for Vx. So this one is given Alice's result, I can calculate what does Bob get. But if I know Bob's result, then I can calculate what is Alice. So that is like the example that we just did just now. Okay, but now we do it in a more general way. So I bring this over, so I got Vx prime minus U Vx prime over C square. This is Vx minus U. Okay, so I want to solve for Vx, right? So I want to put this together. So I got Vx prime plus U is equal to Vx plus U Vx prime over C square. I can factorize the Vx. Right. So finally, I can solve for Vx now. So Vx is just Vx prime plus U, 1 plus U Vx prime over C square. Okay. So notice these two equations, they look very similar, right? So this is the same as this, but I only change the sign. And that is consistent because when I use a positive sign means Alice see Bob moving away in this direction. So if you're Bob, you're seeing Alice moving away in the other direction, so this is you flip the sign. Right, so it's the same formula. but change, flip the sign of u, and then you swap Vx prime with Vx. Right, so I just swap Vx prime with Vx, Vx with Vx prime. What's going on? What's the next fastest thing in the world? Okay. Next fastest thing, yeah. Well, actually, yeah, it's kind of hard to answer, right? Because speed of light is the fastest, and anything slower than that, we separate, in physics at least, right? We classify into two categories. In fact, we call it null particles and time-like particles. So time-like particle is like us, like objects with mass can move at any speed, can be increased. So you can accelerate to any speed that you want, as long as you don't reach the speed of light. So any object can reach anything just under the speed of light. But to go exactly at the speed of light, only light can do that, or massless particles, particles with no mass. Okay. What time are we now? Decelerate a photon. Yeah, you can't. That's the problem. You can't decelerate a photon. Well, yeah, if you argue it in that way, then probably you can. Yeah, so we are supposed to do tutorial in this hour, so let's do the tutorial. Yeah, so let's talk about tutorial 9, right? I guess it is enough special relativity for today. So what we are going to do now is to go back to our everyday life, which is physics at velocity slower compared to the speed of light, which is everything that we are discussing here. Okay, so but actually we are still discussing light, but no need to worry about special relativity. So let's do tutorial 9. Brightness. Okay. Tutorial 9, we stopped until the interference part, right? So tutorial 9, question 9. Okay, any other question to get started? Okay, so tutorial 9, yeah. So let's talk about this type of problem. Coherent light contains two wavelengths. This much lambda and this much lambda passes through two slits separated by this distance. So the interference pattern is on the screen that is 5 meters away. What's the distance between the first order of this light and this light? So just need to calculate them separately. So this one should be pretty straightforward, right? So but I guess let me remind you a few things about the double slit experiment. right? It's been quite a while since we've done this, right? So a double slit experiment is, well, it's a light shining on a screen with two holes, right? So the distance between the two gaps are d, right? And then we shine a light, so we consider what is the path difference between the two lights, right? So the path difference between the two lights, assuming that if the screen is very far away, right, these two lights are almost parallel. So if I zoom out the picture, right, so what I got is my screen is over here, and we take my screen to be the y-axis, right, and then the distance between the light and the screen, the light source and the screen, is called r, right, and then the two lights are shining on the position y at some angle theta. So we have, if the r is very far away, we're going to use the approximation that sine theta is a very small angle, right? So if r is very large compared to this height, then sine theta is approximately equals to tangent theta, and is approximately equals to y over r. Okay, then this is the first approximation I need for my double slit formula, and my second result I will need is, what is the condition for interference? It depends on the path difference, right? We have calculated this in chapter 9. So the path difference is d sine theta. So it's the same theta as this theta. Okay, and then if I want to have a bright fringe, I need to do constructive interference. Right, and then in order to get our constructive interference, we were using the formula that the path difference must be equal to some integer times the wavelength of the light, correct? And then using this approximation, I got dy over r is equal to m lambda, so I can get the position. My formula to get the position of my interference is n lambda r over the distance between the two slits. Okay, so in this problem, we are given that the distance between the source and the screen is 5 meters. The distance between the two slits is 0.3 millimeter, so it's 0.3 times 10 to the negative 3 meters. And the wavelength A is, yeah, so I'll do it here. So for the case of the wavelength A, right, so for wavelength A, which is 600 nanometers, then the first bright fringe is where you use n equals to 1, right? So my y position at A is just 1 times the wavelength, so 660 times 10 to the minus 9, and then the distance is r, and then the d is 0.3 times 10 to the minus 3. You get this position for the first bright fringe. For the other color, for the other wavelength, which is 470 nanometers, so 10 to the minus 9 meters, then we can calculate in the same way. So 1 times 470 times 10 to the minus 9, and then 5 meter distance away, 0.3 times 10 to the minus 3, you will get 7.83 times 10 to the negative 3 meters. So what you want is the difference, right? So the difference is the difference between the two. So this minus this, you will get 3.17 times 10 to the negative 3 meters. So it's 3.17 millimeters. Okay. Yeah, so you guys are burning each other about not having girlfriends and stuff, is it? I suppose that is the stereotype of science discipline, right? Everyone is nerds. But yeah, these are just stereotypes lah. If you meet like actual real physicists, like the ones I met and work with and go to school with, nobody fit any stereotype. Like you see one that happened to be like the stereotype, you know, like the Sheldon in Big Bang Theory. I probably met like one guy in my whole life that is like him, but everyone else is so different. In good and bad ways. Yeah. If you speaking of meeting real life physics students and physics professors and things like that. Okay. What time are we at now? So 10 more minutes. That's true, right? Sheldon is only entertaining if you watch him on the TV, but if you meet someone like Sheldon in real life, you will be super headache and you will avoid people like him. So I guess it's true among you guys now, right? So now you guys are physics students and you interact with each other. So you will see that different people among you have different style and things like that. And so far, none of you guys are like Sheldon also. Okay, so let's do question 11. As far as I know, yeah, nobody in my class is like Sheldon at the moment. So this is another light experiment, and another thing to talk about is the Doppler effect. So Doppler effect might be kind of tricky, so let us do question 11. Question 11 is about a car alarm emitting sound waves of this frequency. You're on a motorcycle traveling away from the car, so how fast must you be to get this frequency? Speed of sound in the air is given, so you don't need to memorize, right? So how to solve this? So the car alarm emits the sound, so this is the source frequency of 520 hertz. You are moving at some unknown speed, but don't know what the speed is. For you'll get 490 hertz. You hear the sound to be this frequency. The speed of sound in the air is 344 meters per second. Okay, so the problem that we are solving is the Doppler effect, where I have a stationary source. And then you are running away from the car. The question says running away from the car, so observer is running away. So what you have here is observer running away, right? And then the car alarm is emitting the sound, right? And the sound should have some kind of wavelength lambda. We can actually calculate this step by step. Okay, so we done this already last week, but 2 weeks ago or last week, let's remind you, wavelength generated by the source. By source of frequency f source, right? So the wavelength generated by source is V is equal to f times lambda, right? So the speed of the wave is frequency times wavelength. This we know is 344. The frequency is given, so we know the formula for the wavelength is just speed of the sound divided by the frequency. So the source will create the sound having this wavelength. But what you hear is different because you are moving relative to the sound. So speed of sound relative to the observer. So this is the observer running at the speed O. So speed of sound relative to observer is equals to what? Okay, so usually, I try to avoid memorizing because every time I memorize plus or minus, I always get the wrong result. But if I think about this situation, I will avoid making mistakes. The sound is coming this way and you are running away from the sound, right? So you are running away from the sound, so the speed of sound relative to you should be reduced. This is how I decide to put in a negative sign. So V minus V0. Okay. If you are running towards the sound, then the sound coming towards you faster, right? Then you plus. But if you're running away from the sound, then reduce. So that's how I decide to put a minus there. So what does the observer measures? Right, so according to the observer, right, so the speed of sound is V plus V0. The frequency that you observe is this. Lambda is just lambda, right? So what we can do is we substitute this. We got the formula for lambda already. We put it into here. So we got V minus V0 is F v over frequency. So we can solve for my velocity. So I want to know what is my v observer, right? So my v observer is, bring this over, I got v minus f0 over fs times v. So my v observer is 1 minus the ratio of these two frequencies times this. So these are all the values I know. Frequency observed you hear is 490. Frequency emitted is 520. Speed of sound in the air is 344. So you will get 19.8 meters per second. Okay, so this is one way to calculate. Right, so I know you guys, probably you read the lecture notes, you memorize the formula, and then you just plug in the formula. That is also true, but I'm doing it this way as part way. Along the way is to recap what we learned about Doppler effect as well. You're missing, wow, so many things. Yes, if he's your roommate, yeah, the Leonard also gone crazy, right? He's driven crazy by him all the time. Yeah, true. That's why I avoided doing that now. Even if I solve it myself, because in my experience, if I memorize the formula and then I plug in the formula, I always get it wrong because I put the wrong negative sign in the wrong place and things like that. Because if your memory is not perfect, right, then you remember things slightly wrong and then you're still wrong. But if you kind of like work it out, then at least when you work it out, you are sure to get at least you are more confident of the answer than memorizing formula. So question 12 is another Doppler, but it has multiple steps. So actually it's quite late already. This question is quite long. So how long do we take to solve? 2 more minutes. Yeah, definitely cannot finish. So yeah, I guess that should be all for today. Right. Question 12. Yeah, at least, yeah, Leonard got a girlfriend. Sheldon got a girlfriend too, right? The other Amy something. Yeah. Formula list. Oh, about memorizing formula, right? Yeah. Okay, yeah. Anyway, question 12 is quite long. I don't have time to, yeah, definitely cannot be done in 2 minutes. But if you memorize formula and plug in, you can get it very quickly, but I kind of want to go through the concept. Otherwise, plug-in formula is plug-in formula, then you get the answer. In any case, I will upload the solution as always. And that's all for today. Yeah, so does anyone have any other question? If not, then that's all for today's class. So yeah, you can exit the session if you want. You mean the Amy and Sheldon? No lah, they're not, right? They're not. Or you mean Leonard and Penny? Oh really? Yeah, I didn't know that. Interesting.